folks. Or as they say at my son's preschool, hello, friends, it's good to see you on this beautiful day. I always like that song. It's very happy. So, oh, thank you. Yes, yeah. So I'm in full-on mommy mode right now because I'm literally like jumping in my car and heading to the airport with my son and my husband right after class. Actually, I need to leave around 2:10. So you're going to see me just like bolt out the door and not have time to talk to anybody today. No office hours today, but I will be back. We are flying out to Iowa to do house hunting and preschool hunting. It's not going to be nearly as fun as Huey would have hoped, though. He asked me the other day, does Iowa have a beach, Mommy? Like, no, nobody. Sorry, this is like, he just, if you go on an airplane, there better be a beach at the end of it, right? Otherwise, if we just hop in the car, that's when we go to, Granny Papa's house, which is up in DeGraspa. Those of you who speak 3-year-old, that sounds perfectly normal, right? DeGraspa? Yeah, no, that's Nebraska. But I digress. So, yeah, full-on mommy mode. I'm happy to see you, though. I happen to have a little bit of intellectual discussion before I switch back into being mommy mode. I have a surprise for you. The homework portal is ready. Would you like to see it? Those of you who haven't seen it yet? Those of you who have, you can revisit it. So on the main website here, we have the portal. And you log in using your last name and your KU ID. Emily, your ID is going to be 123456 because you don't have a KU ID, but everyone else has a KU ID. And I have a bunch of pretend ones that I use for demonstration purposes. So please go ahead and try this out and let me know if you don't get in. If you do, it should get a page that looks like this. Does it work? Everybody's in? Okay, please let me know immediately if not. Send me an email and I will have to track down why you're not in if you're not in. But this is where the homeworks that are not data analyses of individual data are going to be located. So homework 0 is what we're going to do today to demonstrate the system. It's worth 3 points of extra credit for playing along with me. Whenever I return drafts of things, I will post a link to your draft on this page so you can come to this same page to download my feedback. Unfortunately, the system doesn't take drafts up. It can only bring them back, and so that's why I'm asking you to submit via Blackboard otherwise. And you'll have a current total as to how many points you have earned out of how many possible for all the various ways that you get points in the class, as well as your current grade. So if you click on Homework 0, you'll note it says Begin or Continue. You don't have to do these in one shot. You can do as much as you want to at a time, save your work, and come back to it. So you'll get this Begin or Continue link so long as you have not submitted it. So at the top, it will tell you how many points these things are going to be worth, as well as how the points break down across the 2 main sections. Note that if you have data files to download to do analyses with, they will be up here. So there are 2 kinds of questions, what I call computational questions and results questions. Computational questions are things that have numeric responses of which there is a decided right answer. So here's the instructions here. All values to be entered are numeric and must be entered to the nearest 0.001 to be correct. So let's see how many of you remember the syllabus. How many regular homeworks are planned for this semester? 6. So last time I did this class, it was 7, so you guys lucked out. I couldn't make it work with the schedule and the Monday class, which loses a couple this year. So let's say I thought it was 7. That's what's going to happen if you get a wrong answer. The box will turn red. If you enter a correct answer, it turns green. You can try as many times as it takes to make it turn green. And no, I do not keep track of how many times you've tried. I've been asked that before, so don't feel like you have to be embarrassed about not getting something on the first try. How many points total are the homeworks worth? Yeah, 79 this time. How many points do you lose if you submit them even 1 minute late? 3. Yes, it's a steep penalty. I take this seriously because I know things with hard deadlines get done. Soft deadlines get pushed to the back of the stack, and I don't want to be in the back of your stack. So I have a harsh penalty. That way we all try to get this done as quickly as possible, and that way I can go over it right away. That if there's any systematic errors that I'm seeing in the pattern of incorrect responses, I can go over those and we can talk about those. Also, I think I forgot to mention, in the syllabus there is a caveat. I am willing to be flexible with you about deadlines if you are planful rather than reactive. That means that if you ask me at least 2 weeks in advance, I will move a deadline for you. If you know that you're going to be at a conference, or you're doing comps that week, or you're going to be out of town, or whatever is going on in your life that's going to make it hard to meet that deadline, be planful. Send me an email with the deadline and what you propose as a revised one, and I can make it work. So 3 points if it's late. How many points of extra credit do you get for just doing this with me? 3. So 1 free late homework. That's what I'm offering you. How many points from out-of-class quizzes? 21. Yeah, there's going to be 7, and there's 3 apiece. And lastly, how many days are you supposed to be here? 2. So then the other types of questions that you do not get immediate feedback on are these drop-down menus, which I think of as Mad Libs. So where is my office? 3049 Dole, 3042 Dole, or 6007 Dole? It's 42, because 49 is where we are right now. 42 is across the hall, and the 6th floor does not exist. Although my office hours will be here, unless no one shows up, in which case I will go back to my office. My office hours are held. Yeah, after class. The second Tuesday of next week, by the way, is something that my father always used to say when he didn't want to do something. Have you heard that one before? That's a Midwestern expression. So, let's say that I get this wrong. I will show you what it ends up looking like. Actually, I can't do that on my demo. If you get it wrong, what ends up happening is that the correct answer shows up in green and the incorrect answer shows up in red after you submit. So once the due date for this passes, you'll be able to see your feedback. Lastly, M+ is available. All of the above, yes. I believe it is also available through the KU cluster computing, but that is a little bit harder to get access to, and so this is the way that I would prefer to use remote desktop, as well as Watson Library still has it, I believe, although theirs is running version 7 something. Homework assignment should be submitted via Blackboard. Based on individual data, and revision should be submitted via Blackboard. So once all of your numbers are green, you will see a note down here that says good work. However, make sure you submit your other answers. So you can hit this button, check and save your answers, and then you can come back to it to finish it later. You can also hit enter when you're inside the boxes, and that does the same thing. But note that just when you've finished it, though, you have to submit. So there's a box down here that says submit final answers. And then once you scroll down, you'll note that the boxes have gone away so that you can actually read what you've decided the answer is in a paragraph form. And then it double checks to make sure that you did not hit submit final answers by accident. You have to enter your KU ID again to actually submit. So I'll do that here. This is my dummy login, so I will hit submit. And then at the bottom you will get a message that says your answers have been submitted and when you can log in to see your score. So it changes to show you what you got right or wrong, as well as your total points right after the date passes. So all of the assignments are due by 11:59 p.m. on the day of the due date, and so after that you'll be able to see your feedback. And that's it. So any questions? Yes.
I have a question about the program.
Yes. That is, it's the VPN, and it is called KU Anywhere. I can't spell, but it knows what I meant. And so KU Anywhere is the name of the program. So you download it for free, you install it on your machine, and you have to run it in the background. So you will sign into it using your KU ID and password, and then once you're into this network, then you can use the remote desktop from outside campus. Has anyone tried remote desktop for the room yet? Did it work?
Yeah, but I was here.
I'll say then you know how the procedure should work. The VPN is the only other hiccup that would be different between here and at home. So good. Please make sure that you do that at some point within the next couple of weeks. That way, if there is any problem in getting to it, I can troubleshoot that before it becomes a bigger problem. Other questions? The other thing that I did today was to put up your very first quiz. So that is due a week from today by 1 o'clock p.m. That way we can go over it in class. And let me find. Yeah, so whenever there's a quiz due, it's usually on a Wednesday, but a few on a Monday, I think it's noted here. And so you'll log into Blackboard, and that will be available. I do have to provide some background for one of the questions. The first question, which is usually the end of semester question, I decided to make the very first one instead. I want to know what your theme song is. So have you been to like a KC Royals game or a basketball game or something where they introduce the players and they have some walkout music, right? If you were walking out to be up to bat, what would your theme song be? That's what I want to know. So there really are no incorrect answers, although I will tell you that if you give me like a Christmas song or something, I may have to not give you your points for that because that is not correct. But to give you a couple examples, I tend to change mine about every 6 months or so. It corresponds to which class I'm teaching. Previous theme songs of Lisa's have included Motley Crue's Kickstart My Heart, Shania Twain's Man, I Feel Like a Woman, Eye of the Tiger, another classic, Enter Sandman, another one. So it has to be something that has a great beat right from the get-go. And just, you know, it's your theme song. So it helps me get to know you a little bit more. So I'd like you to play along. I'm willing to give you a point for finding out. And then there's a couple other questions over what we've been talking about so far. All right, I think that's my list of stuff I was going to mention. Any questions or comments on any of that? No? Okay. So yeah, let that percolate. Give you a week or so to figure it out. And then we can go back to looking at classical test theory for reliability and validity. So let me pick up with the alpha section. So alpha reliability, slide 23. So this is still something that most journals will expect you to report in some way, shape, or form. I am a pragmatist. GRE people, which is it? Pragmatist. Oh, okay, I like that one even better. So I recognize that you can't fight these battles until you have jobs, and I want you to get papers so that you can have jobs. So it is perfectly fine to report alpha and also report the thing that is more correct, just to keep people happy. I think that's a reasonable compromise. But the problem with alpha is that it assumes without testing 3 things. And I have these listed in order of sort of the biggest problem to the least. Unidimensionality, that all of the items are measuring the same latent trait. That is testable via measurement models that have a latent trait in them. It also assumes that all of the items are tau equivalent or true score equivalent. It means they're all equally good measures of the latent trait. It's conceptualized as equal slopes in the regression type model that links the trait to each item response. And then lastly, that the errors are uncorrelated. So it is entirely possible when you analyze real scales that you may have something that is mostly unidimensional, but maybe 1 or 2 items have some extra wording in common, and they need some additional relationship beyond the trait. That's pretty common, and it's a reasonable thing to do if you can anticipate which items those would be based on their content. But alpha doesn't have room for those sorts of additions, whereas other measures of reliability, such as omega, do. So anytime you end up adding correlations between error terms, you're going to be working against your reliability. So omega reliability, for instance, that we'll get to in the CFA unit, allows you to actually build that into your estimate of reliability. So it still assumes unidimensionality, but it doesn't assume these latter two things. And it's okay to assume unidimensionality if you've done the model fitting to demonstrate evidence for it. So alpha comes from the difference between the sum of the item variances and the variance of the item sum, or what is more directly understood as this. Two things go into alpha: the number of items and the average correlation between the items. That's it. If you want a stronger alpha, all you need to do is get more items without decreasing that average inter-item correlation. It does not and cannot assess the dimensionality of the items because there's nothing in the formula to account for the variation across the inter-item correlations. So we looked at an example, let me see, this slide last time, slide 28. So this is from your readings. It's an example with 10 items that are all equally correlated, so this would be unidimensional and tau equivalent, as well as a variant of a test that has 6 items, some of which are more correlated than others, suggesting 2 dimensions, but nevertheless, both of these scales, these correlation matrices, would have the same alpha of 0.81. So this is the problem with it. All right, so questions on that? All right. So what is reliability for? Reliability is thought of as sort of like a hoop you have to jump through in order to be able to use a scale to do something, but it's also used to quantify the uncertainty around each person's score. So this is something that is not as commonly done, but you will get a chance to do this throughout the semester as part of the output from the programs. You will get standard errors for the estimates of the person's traits, along with best guesses for what their trait is likely to be. And the reliability coefficient is what dictates the size of those standard errors. So for instance, let's say that I have someone who has a true score of 100 and error variance around it of 9. So once we know the total variation of the item sum and we know the reliability, we know what proportion it would be. So for instance, let's say a variance of 9 out of a total of 100 would be 91% reliability. If that's the case, then the confidence interval going 2 standard errors around the estimate of the trait would be 94 to 106. So even though your best guess as to their trait level is 100, there's wiggle around it. And the reliability coefficient gives you a sense of how big the wiggle is. In contrast, if you had something like this, where it was 25, and that means 75% reliability, then your wiggle would go bigger, from 90 to 110. So where this matters, practically speaking, is if you're trying to use a cutoff to make a decision about somebody, right? So you asked me that question, Ryan, like how do we do this? Let's say that you had a group in which you had to get above 100 to be part of it. 100 is not your cutoff. You would have to take anybody whose range includes the possibility of 100, which means that you would be way above or below it as well as just 100. And where this type of standard error thing, to me, is terribly, terribly striking is when the GRE changed its format. So I'm dating myself again. I took a GRE. I was one of the first cohorts to take it like electronic. That's how old I am. And then it changed not only from being electronic and adaptive, but changed its scale. So when I think GRE, I think like mean 500 and standard deviation 100, but now it's mean, 150, standard deviation 10. And I was asked to give a presentation for PsyChi, which is the Undergraduate Honor Society, about the changes to the GRE in terms of the scoring and the format. And as preparation for that presentation, I downloaded the GRE's Guide to Interpretation of Test Scores, that ETS, the company that makes it, published, okay? So this is straight from their mouths. And what I found was shocking, because when you get your GRE test scores back, you don't get your standard error with them. Do you ever notice that? And Lucas is like, uh-huh. So And what are GREs used for? They're used for graduate school admissions. In some cases, you have to have a minimum score to get in. In other words, people rank order candidates and assign scholarships and funding based on your GRE scores. So I've been part of discussions where, well, this person's GRE was only 550, but this one's was 600, so that must mean they're much smarter. Actually, no. The GRE is supposed to predict graduate school success, and it doesn't even do that. But here are the published ranges from the last time it was on that 500 scale, which would have been maybe 2012-ish. So it's a little bit old data, but the same problem still exists on the new scale. I took their manual and what they said their standard errors were at each level of a possible score, and I computed 2 standard errors above and below that. So this is verbal. So here is the range in which the mean would be. If you got, let's see, a 550 score, that means that it's actually anywhere from 485 up to 615. So those arguments about the person who got a 550 being different than a person who got a 600, nope. They are indistinguishable with the level of reliability that the test has. But who cares about verbal, right? That's not relevant. How about quant? Quant's important, right? It's even worse. At the middle of the test, the standard error is 55. So that means a score of 500 is anywhere from a score of 400 to 600. Pretty much the entire range of the applicant pool that we would have concerns about. Yep. Yes, sir.
So the scores, are they being measured against some performance? So how can you say that a 550 is not equal to 600?
You can't. People are just looking at the means. Basically, the score that you get back is the algorithm's best guess as to what the mean of your distribution would be. Each person really has a distribution of possible traits, and what it's outputting is the mean or the mode of that distribution, some measure of central tendency. And what isn't being reported is the variability around that range. And so that's what these pictures are showing, is that for a score of 500, their best guess as to what your total distribution around it would look like is 4 to 6. And people who don't recognize the size of the standard errors want to be able to make these gradations between people to say that 600 is greater than 550, like significantly, meaningfully, but it's not. Not by the makers of the test themselves. And these people sleep on a bed of money every night. ETS is a billion-dollar company. And so there was concern when the scoring system changed that there were fewer possible scores in the new system. But if you look at how wide these intervals are, it's like, who cares how many scores there are? They don't know what this is. And there's all this language within the manual that says things like, you should not use this to compare applicants, or you should not use this to categorically deny entry to graduate school. The people who made the test say these things as a CYA maneuver, but that never ever made it down to like the faculty who look at these things and make decisions. So the levels of reliability that they report, this is the level of precision that the score is. And we will see lots of examples of this. If you give, say, a 4-item test, you might actually get a reliability coefficient that's greater than 0.7 or 0.8. But when that translates into a standard error, it's basically like any score has the entire range of possibility around it. Like the real number line is your standard error. So this is something to keep in mind. Reliability has a purpose. It's to quantify the precision with which a given score is estimated. And that's really what's important here. By the way, this can't be true. They are reporting that people at the top have a much narrower window. They do that because they know that the score can't go above 800. But that's never going to be the case, that the people at the extremes are better measured than the people at the middle. So make sure your advisors know this. The GRE, not all it's cracked up to be. Which is why I almost pretty much completely disregard it when I look at applicants. You know what I look at? Their statement. Number one, is it grammatically correct? Number 2, do they have a clue what they want to do and why they want to go there? That's it. To me, those are the biggest things. But that's an opinion. I could be wrong. So, thoughts, questions on that? Striking, huh? So another problem with reliability is that people often talk about, say, inter-rater reliability using the Pearson correlation between two raters. That's not actually right. If you want to compute coefficients of reliability across multiple ratings, the more correct way to do it is intra-class correlation, which is actually a proportion of variability due to raters as opposed to subjects, as opposed to items, and so forth. So let me show you an example. Pearson correlation does not take into account changes in the mean or the variance between two variables. It standardizes them. But that's problematic if you're trying to keep track of actual distances in scores between two raters. So let's look at this example right here. Let's say one person, they have a mean of 97 and a standard deviation of 15. The other has a mean of 100, standard deviation of 15. So pretty much. So the Pearson correlation and the intra-class correlation between these two sets of data would be about the same number, about 0.68. But what if the second person or the second test is systematically higher? That is disagreement. Particularly if you're looking for people to get into your group and one person's ratings are all uniformly higher than the other person's, that's going to mess up who you decide to take into your group, right? Pearson correlation does not pick this up. It removes differences in mean and variance before looking at the association, whereas intra-class correlation does pick this up. So if you are in a position to examine inter-rater reliability, come talk to me, because I can hook you up with some SAS programs that I've already written that do this. And it's particularly handy to think about it from this intra-class correlation framework when you have more than two raters, and for which, like, how do you do a correlation amongst three people? You're like, how does that work? It does work, because it's phrased in terms of proportion and variance. So just keep that in mind when you're thinking about reliability. If there are differences in scale, then that counts as a disagreement, as well it should. Other kinds of correlations. KR20 is sometimes listed as a measure of reliability. That is alpha with a computational shortcut for the fact that it's binary items. It's literally the same number, so it's not a separate thing. And this was invented in 1937, and it's still around today. One of the issues, though, when you do have binary items, or even ordinal items with maybe 3 or 4 categories, is that your reliability coefficients are going to be smaller than if you had truly continuous data because of range restriction. So in binary data in particular here, the maximum correlation that two variables can have is dictated by their means. Only when both variables have means of 50-50 can you possibly have the full range of correlation of -1 to 1. Otherwise, this chart shows what the maximum correlation is. So if 10% of the people in X have a 1 and 20% of the people in Y have a 1, the most those two variables can be related is 0.67. So if your alpha doesn't look so good for binary items, this could be one of the reasons. The same problem is still going to show up in measurement models, but they're going to base the analyses on a different kind of correlation instead of a Pearson correlation. So here are all the different kinds that you may hear about in the context of assessing reliability or correlations between items within the same scale from which reliability is derived. So Pearson correlation, you know that one, right? That's supposed to be for quantitative variables or continuous variables. I'm going to go with phi correlation. Sometimes I feel like saying phi instead. Any takers, opinions? Phi or phi? Phi, phi, fo, fum? Doesn't matter because it's equal to Pearson anyway. Point biserial, that's a fancy one. That's a Pearson correlation between a binary and a continuous. So above the line, these are synonyms based on different types of items, but they all equal mathematically to a Pearson correlation. The ones below the line, which I have labeled the line of suspended disbelief, are not equal to Pearson correlation, and these are going to show up in our class in the context of categorical items. It sounds crazy when phrased one way and totally reasonable when phrased another. So the tetrachoric correlation is the correlation between the pretend underlying continuous distributions of what is actually binary data. Like, what? So if I drew a nice happy little bell curve on the board here, like pretend that this is what my item really is in reality, but I screwed up. I dichotomized it. The tetrachoric correlation is supposed to be the correlation between the true underlying variable, even though I only have a binary representation of it. That sounds crazy, right? Doesn't that sound crazy? But if I say, no, it's the correlation between the probit. Oh, okay. Then that sounds way less crazy, or logit, as it were. It's probit in this case. It is a way of reconstructing a correlation based on the categories. So if you have, let me draw, actually I'm going to get paint out. Why not? So you're going to see this throughout the semester. Here's paint. Paint 3D, because, 2D was insufficient. Still looking for the spray can. Haven't found that yet. So if I had data that look like this, basically. I'm trying to make my little scatter plot here. That's the best way I can draw a correlation of 0. If I wanted to draw a correlation of positive, I'd make a scatter plot that has this shape, right? So I'm drawing these axes here to remind you that between two binary items, there are 4 possibilities. No, no, yes, yes, no, yes, and yes, no, right? And you know from the data how many people are in each of those categories. So if you think about those data, those frequencies, as being some kind of measure of mass, what a tetrachoric correlation is trying to do is to figure out what the correlation pattern would have been to create those unique distributions of probability. So if there is no association between variables, you would expect 25% of the outcomes to be in each of these quadrants. If there is a perfect association, then everybody is going to be up here or down here. So a tetrachoric correlation is trying to infer, based on these frequencies, what the underlying correlation would have been. That sounds less crazy, right? But tetrachoric correlations are better ways of summarizing relationships between binary data because they do go from -1 to 1. So they don't have the same range restriction problems. Related to that, in the context of what is going to be called polytomous data in IRT, which just means like ordinal, you have polychoric correlations, where you have multiple thresholds for all of the possible differences between items, but it kind of works the same way. And then there's also biserial, which is a really actually continuous variable and either a binary or a, binary in this case. There might be like polyserial for the other one. So models that work with link functions, which include IRT models, logistic models, probit models, tobit models, all of those things, they're working with one of these other kinds of correlations as a measure of association that take into account the boundaries, and they solve the problem differently. So this is to say, when you run your Pearson correlations across your items, they're probably going to be lower bound estimates of what the actual relationships are, to the extent that you have these range restriction problems. What else? All right. How are we doing? I feel like I'm way more excited about this than you guys are. Is it just me? It's okay if that's true. I mean, I did pick this for my job. That's because Janet Jackson backup dancer was already taken, and that would have been my first option, but as it turns out, that was not in the cards for me. But yeah, if there was ever like a contest of like, you know, what is it, I'm trying to think of, like the reality shows where like, you know, you can pick your husband, you can pick your house, you can win all this, right? Like, which 40-year-old woman who formerly used to dance in high school wants to be a backup dancer? Like, if there was ever a reality show like that, I would be like, I'm sorry, guys, I'm done. I got to go pursue my dream. But no, this is where I'm at, and I actually do like this stuff, so it's okay if I'm excited. My goal is that eventually you will be excited too. Yeah, I saw Janet in concert finally last year. She kept delaying her concert. It was so awesome. It was so awesome, and she's like 50. So you think I'm old. So yes. So when you're characterizing items then, back to the show, there are two characteristics that differentiate items that I want you to learn the vocabulary, because these ideas are going to show up in each type of model we're going to talk about. They do show up in classical test theory to the extent that you end up with a bad alpha and you're trying to do some homework to figure out which items need to go. So the two properties are difficulty and discrimination. You probably have seen item difficulties if you give multiple choice exams and the testing company sends back item difficulty as the proportion passing, for instance, or just the mean on an item. That's what difficulty is in a classical test theory context. So if it's binary, then you can think of it as just a proportion passing. Otherwise, if it's ordinal or quantitative, then it's just the mean. And this differentiates how difficult or severe an item is. And note that the direction is logically backwards. So if I have an item that 90% of the sample passed, that has a high difficulty because it has a high mean, but an item where 90% of the people got it right, that would actually be easy. So it's logically backwards. Even though it's called difficulty, it's actually easiness in this context. It's going to be backwards in CFA, and then finally in IRT it's going to turn around because the equations have a minus sign instead of a plus. So keep that in mind. Difficulty is actually easiness in this context. And this is typically ignored in classical test theory other than as a way to, if an item is too high or too low, then it might get thrown out for that reason, although that's actually not a good idea. We'll talk about later. The one that is paid attention to more in this context and in others is discrimination. How related the item is to the trait. So it's eventually going to be some sort of slope in a latent trait model. For now, it's just a correlation of that item with the total score for the scale. And it's either the total score or the total score minus that item, depending on how you do it in the program. And bigger is better. The more related that item's response is to the total score, that's supposed to be a better item. So items that have low discriminations would be candidates for removal from a scale, and they would be the reason why your alpha is bad. So here's a few other things that you may have come across, and I want to give you a sense of what the assumptions are for these. How to predict how reliability would improve if you had more items. There is a formula by which to do this known as the Spearman-Brown prophecy, and here's an example. So if I had an old reliability coefficient of 0.4, no one would say that's good enough. Well, what if I took 5 times as many items? Well, I can anticipate that my new reliability would be 0.77. As indicated by bold text here and underlined, this formula assumes the items are parallel. Not only are all of the items unidimensional, equally discriminating, tau equivalent, but they have equal error variances too, which is stricter than just regular tau equivalence. Parallel items is really, really hard to get in practice. So alpha requires tau equivalence. that translates into equal covariances, whereas Spearman-Brown assumes parallel, which is equal correlations. So equal discriminations plus equal error variances. All of these things, by the way, I will show you how to test as empirical questions in the analyses we're going to do. Attenuation-corrected correlations you will also see. So if you have a correlation between two variables, but each of the variables itself is not perfectly reliable, how do you anticipate the effect of that unreliability on the relationship? So from the original paper, by the way, where I think this is like 1901 or something, an old correlation of 0.38, but if we have an estimate of the reliability of each of the variables and it's low, you can use the formula to compute what the reliability would have been between just the reliable parts of the variables. And that works out to be an unattenuated correlation of 1.03. Not only is it strong, it is better than perfect. It's like you kicked it up to 11. And this sounds crazy too, but this is exactly what SEM is trying to do. It's trying to take the reliable, the good part of the construct out of the items and look at relationships among those parts. And where it starts to be unreasonable is when the part that's reliable is so small relative to the total information in the items. So SEM can't save you if you have very unreliable data. Yeah, I don't want to talk about that. That's enough for that. So wrapping up, classical test theory is just the idea that you can take items, add them together, and then use very strict assumptions to delineate how much reliability there is in that total score as a differentiation between true score and error. You can't do that with a lot of simplifying assumptions. One of the things that makes this problematic is that that total score then is not comparable across time or samples unless it's exactly the same items each time. The total score doesn't know how it was made. It's item specific. To make classical tests more reliable, what kind of items do you need? More. Because the total score doesn't know how it was created, there's nothing about this that takes into account differences between items and how well they are related to the latent trait as well as how difficult they are. The only way to get higher reliability coefficients is to have more items, and it doesn't matter what kind, just more. That is going to stop later on. And the other thing that is notable about this framework is that when you get a reliability coefficient, you get 1. If I have an alpha of 0.8, that is implicitly assuming that everyone along my trait is measured equally well. But that is unlikely to be true, because if most of the people are at the middle and most of the items were selected to have means in the middle, then the people at the extremes don't have as many items that are targeted for them. So we don't know how well somebody who's at the top or the bottom is going to be measured if they're at the floor or the ceiling of the test. So this single estimate of reliability is an oversimplification in most cases. And that still shows up in CFA, but it changes in IRT. In IRT, what you end up with is a reliability function known as test information that literally tells you at every point along the latent trait continuum what your reliability is. So then you can evaluate for the purposes of the measurement whether that level of reliability at that point on the trait is good enough. So we will see lots of pictures of those test information functions later on. All right. So, is this stuff new or is this old? No one's asking questions, which either means you've known this before or you don't want to know any more. It's new to you? Heather, it's new to you? Yeah, did you have any idea alpha was so terrible? No, or that the GRE was so useless? You knew that, right? Everybody knows that. Yeah. I still remember my experience taking the adaptive test, the verbal. I started answering questions, and all of a sudden the questions were like, black is to white, as big as 2, and I'm like, I'm not doing very well, am I? Nothing like the proprioception of sucking while you're trying to climb out of the cellar that the adaptive algorithm has oriented you to, right? But yeah. Tyler, what do you think? Have you heard this stuff before? You came from a measurement program. He's another one with the done kind. He's a postdoc here. So we all introduced ourselves the first day. Talked about the importance of having the done kind of the dissertation. So you were saying, you've had this stuff before?
I have, yeah. I remember I teaching a course undergraduates about measurements. Teachers who would try to focus on that.
Yeah, it's really important in the context of education to have teachers who are trained enough to understand what to do with the information that's coming back from these high-stakes tests, right? Do they get standard errors on their printouts? Not usually, yeah. So I shouldn't take it personally. Maybe it's just dry. Yeah. What else? Adrian, what do you think?
It feels like we talk about alpha a lot in psychology in terms of like how we measure like certain traits and whatnot, and so this is probably like the second time I've ever been exposed to the concept where it's like alpha is pretty bad when you look at other forms of like measuring reliability.
Yeah, it's alpha is bad if the measure doesn't support the assumptions it makes, right? But like if you actually get it right, like if it is unidimensional and all items are equally good and there's no correlated errors, then the more complex measures actually simplify to alpha. It's just that there's nothing in this process of adding shit up and throwing it at SPSS that allows you to detect when the assumptions are being violated. That's the problem, right? It's not a testable framework. So yeah, it's the ASU measurement model, as I call it, the add shit up measurement model. But not to be confused with Arizona State. They wouldn't do that. They know better, but just ASU.
U of A does. Same.
U of A does. They add shit up. Well, you know, there's lots of variation across campuses. I just didn't want to like somehow misattribute like that, you know, Arizona State is responsible for alpha and all of its horrors, right? That's not what I'm saying. This is just my own little acronym for add shit up. But yeah. So, yes, Betsy.
Yeah. So most of the things that you were showing us today are things that does this fall under the umbrella of like stuff that you don't like?
Yeah. Yeah. What gave it away, right? Yes, I have a lot of opinions, and I am going to try throughout the semester to delineate which ones are sort of like, this is how I think I might be wrong, versus, no, this is math. And like to the extent that you can do math and show that something is wrong, like that's the problem that I have with this, is that there's nothing within this framework that allows you to verify that what you're doing is reasonable. You just have to believe.
So based on what you were drawing like on paint and that like when you were looking at
The tetrachorix?
yeah. So
Yeah.
my lack of knowledge to show here, but is that good or bad? It seems like weird. How I don't know.
Well,
is this something you would recommend to do to evaluate something or
yes. Yes with the star behind it. So it's the whole point of a latent trait model is to try to capture that the reason for the correlation between items is due to one or more traits. Like, and you say, well, the reason that these items are correlated is because they measure that, and the reason that those items are correlated is because they measure this other thing. So a logical precursor to doing that is that the items are correlated in the first place. Because if they're not, game over. Like, you can't have a trait because the whole job of the trait is to predict the correlation. But looking at patterns of correlation can give you a sense of whether or not, like, you're heading in the right direction, even before you do any fancy analyses, because you can always look at correlations no matter how small your sample is. And indeed, when I start off on things, that's the very first thing that I do, is I stare at a correlation matrix and try to get a sense of what the data look like is going to happen, because it's foreshadowing. But where that goes awry is when you have something like this with binary items, you know, I might look at a correlation of 0.17 and be like, oh, that's terrible. Those items can't possibly measure the same thing. But if the items, only 10% has a 1 in this variable and 80% has a 1 in that variable, that is the highest possible correlation that variable can have. So Pearson correlations are not always appropriate to the extent that they can't sort of stretch this out and be sort of like out of the maximal relationship you could have, how much of that did you get? And the tetrachoric is designed to not have that difference in max or minimum. Where's my picture? Even if you have items with two different means, you should still have a theoretical max of -1 and 1. And that, so it's better in that sense. Does that help?
Yeah.
We'll get there. But point being, you can ask for this. So you can ask for this in M+, you can ask for this in SAS Proc Freak. There is a, I think it's polycore is the option. So when you're dealing with these kinds of range-restricted items, a better way of just summarizing their relationship is tetrachorics and polychorics. Question?
Yeah, the 0.1 and 0.8. If they're binary, like basically wrong, 0.1 would like suggest that you got it wrong. 0.8 suggests that you got it right. And then correlation is like, I always say, think of it as like, like if someone scores high in the mean for one thing and high on the like really high on the second thing, then they're going to have a high correlation. But if someone gets one thing mostly wrong, one thing mostly right, how can they have those two things be correlated, you know, higher than correlated? You know what I mean?
Yeah, I do. And it can happen because the items themselves vary in difficulty. So if you have an item that's really hard, it's sort of like tautological. Like, how do you know it's hard? Because only 10% of the sample got it right. It's like, well, then, is it just that you have, like, dumb people, or is it a really hard item? And the fact that there's other items that they got 80%, that's either an easier item or you have smart people, right? You can't piece it apart. But when you have items that deliberately vary in their difficulty or their severity, you can end up with patterns like that, where only 10% of the people got the harder item right, but a lot of people got the easier items right. And those items, even if they're measuring the same trait, can't relate to each other as strongly because of that.
So this is able to sort of keep that out.
It does a better job. I don't think it's a panacea. I mean, to the extent that you don't have a variable, you have a constant, like the lower the mean gets, the less likely you're going to show any kind of relationship whatsoever. It's better. I'm not saying it's perfect. But you can sound extra smart by talking about tetrachoric correlations, so that's a fancy word. Or polychoric. What's the new word I learned today? You told me?
It's pragmatist, right?
Pragmatist. Pragmatist or pragmatist? That's like a Minnesota version of it, isn't it?
Oh, yeah, I'm from Wisconsin.
That's what it is. That's like when I say like Megan or egg or bag, like a shopping bag. Yeah, that's okay. So that's the Wisconsin pragmatist. I got it. All right. Yeah. Good. Well, I am a pragmatist, and Lisa Pragmatist says that it's time to go so she doesn't miss her airplane. Because I hear Iowa has great beaches. So.
Are there natural lakes in Iowa? Because Kansas has none.
Well, there's a river running through it. I know it flooded like 10 years ago and ruined everything. That's what I know. But
It's close to Lake Michigan.
yeah, so I will not see you guys on Monday because it's Labor Day, but I will see you a week from now. Please do your first quiz at some point in the next week and catch up on your reading, and then we'll look at the example next time. So, thank you.
Safe travels.
Thank you.